go ahead and get started. Now I have to decide where we're starting. Trig stuff, other stuff. Let me give you all a warm-up problem. To try on your own. And I'm going to do something that involves our fundamental theorem of calculus, but I'm going to keep it pretty straightforward. Let's integrate from 0 to 2, 5x to the 4th minus sine of pi x. Good times. Let's try to keep things in focus. Awesome. So I'm going to give you all a couple minutes to give that one a shot. I'm going to try to zoom in a little bit. That'll work. Okay. And remember that if we, just like with derivatives, if you have addition or subtraction, you can break that apart into two pieces. You don't have to try to treat it all as one piece, and you shouldn't try to treat it all as one piece. Definitely want to break that up. And even if you're not sure what to do with the trig part, you can always try the first part by breaking that up into two separate integrals. How are we doing? Can I ask some questions? Are we all in the trig? Okay, we're in the trig. Should we do the trig together? Yeah. We're avoiding the trig? Okay. Okay. So definitely what's happening in the room is people are avoiding the trig, and we should do that part together. So let's tackle this thing together. Well, this first part, this is one of our like basic antiderivatives, just like with our basic derivatives, but in reverse. So I'm going to add 1 to the exponent and divide by the new exponent. The 5s will cancel out if we like. And then the extra new part with the fundamental theorem of calculus is that I'm plugging in the 2 and subtracting, plugging in the 0. So I'd end up with 2 to the 5th minus 0 to the 5th, which is 32. Now on the trig part, we've got options. One option is to do a U substitution. The other option is to just remember the pi as a number. So if that said 3x inside, then when we take the antiderivative, we would divide by 3. So we're just going to divide by the pi. So if I take that approach here, then I'm thinking about whose derivative is negative sine. And the function whose derivative is negative sine is positive cosine. Calculus can never change what's inside of the trig function. So we're going to leave the pi x there, but we are going to divide by pi. And then we're going to go from 0 to 2. Don't have to do this, but I'm gonna kind of think about that 1 over pi separately. And then this will look like cosine of 2 pi minus cosine of 0. Now I would say both of those are like numbers we're supposed to know. Cosine of 2 pi is equal to 1, but cosine of 0 is the same. Oops, I said 0, I wrote 0 because I was saying 0. Brains are weird. Cosine of 0 is also 1. So this whole thing goes away. So my final answer would just be 32. And there's a question in the chat about how I knew to divide by the pi, and it is because it's just a constant. So like if we were to quickly take a look at our trig stuff, if I integrate cosine of some number times x, what I get is 1 over that number times sine of the number times x. If I integrate sine of some number times x dx, I get 1 over that number times negative cosine of that number times x. Now we didn't need that negative in the previous problem because it was like already part of my question. Since we're already on a roll with this, I also want to point out that that same kind of thing happens when I have like e to the ax dx and I'm integrating. I get 1 over a e to the ax plus a constant. And that's always happening because essentially we're counteracting, we're going backwards from the chain rule. So chain rule with derivatives, if I have a number times that x, we'd end up multiplying by the number. And because we're doing antiderivatives, we're going backwards. So instead of multiplying by something, I'm dividing by it. Good times. I would like to do something along the lines of problem 1 on the homework next, because it is a fundamental theorem of calculus kind of thing. But I need more space, so I need a fresh sheet. Problem 1 on the homework is a definite integral because it's got numbers and it's got an absolute value in it. So I'm just going to make something up and I'm going to say absolute value of 3x minus 6 dx, and I want to integrate this from 2 -2 to 8. There's a long way to do this, and then a longer way to do this. The way that I would approach this problem is to think about what this is telling us as a definite integral. And as a definite integral, this is saying, what is the area under y equals absolute value of 3x minus 6 between x equals -2 and x equals 8. That's not how we read it, right? I read this as the integral from -2 to 8 of absolute value of 3x minus 6. But this is what it means from a fundamental theorem of calculus perspective. I like pictures, so I'm going to get a picture going because I actually think that's the easiest way to do this problem. So if I need to sketch y equals the absolute value of 3x minus 6, I'm going to start by figuring out the intercepts. And if I set y equal to 0, then that means 3x minus 6 needs to be 0. And I'm going to get that x is 2. So if I come over here to x equals 2, that is kind of the tip of my v. So what this picture, so now going from the picture to what this actual question is asking me, this is not going to be to scale, but you all will survive. This is saying that I'm going to go as far to the left as -2 and as far to the right as 8. And I want to take all of that area. So we have a choice. We either use geometry or we break this integral apart into 2 pieces and do calculus twice. That's why I said there's a long way and another long way. You just have to pick which long way you prefer. So if I go geometry style, by the way, you would get full credit for doing this geometry style because that is the way our textbook does it. If you were in 21B, our textbook would do it calculus style. But for 16B, our textbook goes geometry style and says, great, that first triangle, well, if I want to get the area, it's 1/2 the base times the height. So for that first triangle, I'd have 1/2. My base here is 4. And to get the height, I need to plug -2 into the function. So 3 times -2 is -6. -6 minus 6 is -12, but it's inside of an absolute value. So that means that's at -2, 12. So my height would be 12. Then I would add that to my second triangle. And for my second triangle, the base is 6. So I'd have 1/2 of 6. And then to get the height, I'd plug in 8. So I'd have a height of 3 times 8 minus 6. So 3 times 8, that's 24. Minus 6, 18. So that would have a height of 18. Question?
So for the base, it's basically just seeing how far is it, and then for the height, subbing in for the x.
Perfect. So to recap for those of you on Zoom that might not have heard that, the base is basically just counting how far apart they are. And for the height, it's subbing the x value into the function to get a height. Now, I said there were two options. So if we go calc style,
Is
Which-
that for the geometry?
yeah,
You just simplify it.
yeah, that's it. If we go, yeah. And this is definitely the method that the book expects you to use.
Okay.
Yeah, for sure. But if you really felt like going calculus style, then what we end up doing is treating this absolute value of 3x minus 6 as a piecewise function. So if x is greater than 2, then what's inside the absolute value is already positive. So we don't actually need the absolute value anymore. So this would just be 3x minus 6, anywhere that x is greater than 2.
I think this is what you showed us.
Okay. Now, if x is less than 2, the absolute value, well, let's pick a number that's less than 2. So if I pick 0 and I plug it in, then what's inside of the absolute value is negative. And the absolute value then switches the sign because it was negative. So we're going to switch the sign like this. That means that we've got to take our first integral that went from -2 to 8 of absolute value of 3x minus 6 dx and turn that into something from -2 to 2, where we actually swapped the function out for negative of it. And then from 2 to 8, we use the original 3x minus 6 because the absolute value wasn't doing anything for us. And now you have 2 calculus problems to solve. But you'll get the same answer. And for sure, the textbook does it geometry style. Yeah.
Is there times when we can't use the geometry style?
So the geometry style only works if you know how to find the area of that shape, right? And so absolute value is one where we know what the area is going to look like. It will be triangles. Now the flip side of that question, are there times when you have to use geometry and not algebra? For sure. But our textbook really only gives one specific example where that's the case. And that one specific example would be if I asked you to integrate from 0 to 3 of the square root of 9 minus x squared dx. This is actually not something that we can integrate. Now we might think that we can integrate it, right? Because I can rewrite that as like 9 minus x squared raised to the 1/2 power. The problem is the x squared inside. I would have to have a u substitution to make that work. So if there were an x out in front, then I could integrate it. But this thing, I can't integrate. So in this same section of the textbook, the trick is to recognize that that means our function was like y equals the square root of 9 minus x squared. But if I square both sides and then add the x squared over, it's a circle. So this is equivalent to thinking about this circle with a radius of 3. But because it's only the positive square root, it's only the top half of the circle. And then if we wanted the area from 0 to 3, it's 1/4 of the circle. So the answer to the integral is 1/4 of pi times 3 squared. And this is the only example that our book gives us anyway, where we have to use geometry. we actually can't integrate this. In the next section or two of the book, we will have other methods to deal with stuff that we can't integrate, but at the moment, all we got is geometry. Yeah. Dun, dun, dun. Good times. How are we feeling? Better about that other one? Okay, good deal. So where we go from here? We can, should we practice some more trig stuff? Practice some more trig integrals? Do a few quick examples. Let's get some trig practice. And by the way, the trig problems, you know, maybe they're going to be definite integrals, maybe they're going to be indefinite integrals. Let's just practice some indefinite integrals at the moment and not worry about plugging numbers in for the endpoints. I can make these ugly, but a lot of times, even the ones that don't look so ugly require a little finesse. So let's say that I had do we want something a little messy? So tempting. I'm going to make this a little bit messy. Sine cubed x, cosine cubed x dx. I'm going to walk up to this integral. And the first thing that I personally might do is actually rewrite this for my own sanity as sine of x cubed times cosine of x whole thing cubed. You don't have to do that, but sometimes it just helps me to switch it up visually like that. So I'm looking at this, I've got sines and cosines. So I'm thinking there's probably a u substitution hiding in there for me. So if there were a u substitution hiding in there for me, what might you think of letting u be equal to? Sure. So if I let u equal sine of x, then my du would be cosine of x dx. But there's a problem. I don't just have one cosine, I have three of them. So the way that we're going to deal with this is by the help of a trig identity. So we're going to think about that u substitution. I'm going to kind of have it on pause there. I'm going to take that cosine cubed x. I'm going to borrow one because I know that I need it for my u substitution, but that's going to leave me with a cosine squared. The reason that that's helpful is we've got this fundamental trig identity that cosine squared theta plus sine squared theta is equal to 1, which means I can swap out the cosine squared for 1 minus sine squared theta. That's not a u substitution, that's just trig. So I'm going to rewrite this to say sine of x cubed times 1 minus sine squared x times cosine x dx. And now I'm ready to make my u substitution. So the cosine x dx, that's what I get to swap out for du. Sine cubed is like u cubed, and 1 minus sine squared is 1 minus u squared. I will give you all a minute or two to finish that off. My recommendation is to distribute the u cubed. Should I catch up? So if I distribute this out, I've got u cubed minus u to the fifth. And that's, oh, I don't need an integral. I'm ready to evaluate. Ready to take that antiderivative, add 1 to the exponent, divide by the new exponent, minus add 1 to the exponent, divide by the new exponent. And to make sure we get all our points, we should put this back in terms of where we started. Since u was equal to sine of x, I would choose to write this probably as 1/4 sine to the fourth minus 1/5 sine to the fifth. That is not the only way to write that. You can totally put stuff in parentheses with exponents outside. You can leave it as division by 4 and division by 5 instead of rewriting it as a fraction. That's all just like personal preference. We have about 20 minutes left. Do we want to go back to some finding area problems? Do we want to see the new stuff that's going to be finding area problems between two curves? Unless you already did that, but according to his syllabus schedule, that's what you should be seeing this evening. New stuff, old stuff. New stuff, area problems is the vote on here. So let's talk new stuff. And new stuff lets us keep practicing old stuff. Don't worry. Okay, so far the area stuff we've been doing with fundamental theorem of calculus is like the area between a graph and the x-axis. But let's spice it up a little. And here is y equals x squared. And I'm going to try to draw this well. We'll see if it works out. Here is y equals 2 minus x. And what I want to find is, oh, wish I had my lighter pens. I usually don't like my lighter pens, but today I wish I had them. I want to find the area in there. So there are two ways that we can think about finding the area in there. And I'm going to show you both ways, but one of them we're not going to use. So I don't know if you actually want to write stuff down or not. But I'm going to show you the way we are going to use first. And then if you really don't like it, I'll show you the other way. So I'm going back to anytime calculus style, I'm thinking about area. I'm thinking about this as rectangles. I'm thinking about a height times a base. So if I draw in an arbitrary cross section right here, and I've got some kind of a rectangle. Oh, will you all forgive me if I change my 2 to a 12? So make sure you change it in your notes, or you're going to look back later and not know what happened. Make it a 12, not a 2. So my picture's not perfectly to scale, but whatever. So if I told you that right here, my x was equal to 1. Yeah, that'll work. I want you to find the height of the rectangle I drew. So if my x value right there is equal to 1, how would we go about finding the height of that rectangle? Yeah. Okay, I like that. We can plug it back into something. So if I plug the 1 into the 12 minus x, what height would I be at? What's that? 12 minus 1. I try to keep the numbers easy. 12 minus 1. We're at 11, right? Okay. So right here, the height is 11. But that's not actually the height of my rectangle. Because my rectangle doesn't come all the way down. It starts right here. Where do I need to plug in the 1 to find like where the bottom of the rectangle is? Totally. And if I plug the 1 in here, I'm going to be at a height of 1, which means the height of that rectangle is actually how much? Yes. And we're getting that 10 by thinking about the top height minus the bottom height. So if we translate that into like calculusiness, then my area here, I'm going to get by thinking about the height really is like the line minus the parabola. Add them up calculus style, a little bit of dx. So I'm going to get my area by doing the integral of my line equation minus my parabola equation dx. But if we actually want to get the area, this has to be a definite integral, which means I need limits of integration. I need some numbers here. Oops, sparing my ink. I need some numbers here. One of the numbers I can get just by looking at the graph, right? Because I only shaded in as far as the y-axis, which means I only shaded in as far to the left as 0. But to get the other limit of integration, I need to know what the x value is over here. Anyone remember how to find the intersection of two curves? Cool, we can set them equal to each other. So we're going to set the two y values equal to each other to get that intersection point. So I'm going to set the y equals x squared equal to the y equals 12 minus x. I made it a 12 because I wanted it to factor. So in general, if I'm going to solve a quadratic, right, my first starting point, unless you're going to complete the square, which no one wants to do, or I'm sorry, if you wanted to do it, you can complete the square. I don't want to do. I want a 0 on one side or the other. I need a 0 if I'm going to factor, and I also need a 0 to use quadratic formula. So I would rearrange that to say x squared plus x minus 12 is equal to 0. And I strategically chose the 12 because I needed something that I knew was going to factor. And this should be a minus 3, a plus 4. Which tells me that there are two places that they intersect. They're going to intersect when x equals 3, and they're going to intersect when x equals -4. And actually, because I gave us a graph, we can see that they intersect over here and over here. But I'm only interested in the part right here, which means my upper limit of integration would be 3. Should we practice finishing that off? Yeah, you're gonna practice or I'm gonna practice? Together, we're gonna practice together because it's Friday. We're all one big calculus community. I like it. Okay. There is just a lot going on. It is kind of a hot mess of parentheses in here. And I am someone that needs my math less cluttered in order to think. So I'm just going to write this as 12 minus x squared. No U substitution required because they're all just separated by addition and subtraction. So I can take each piece individually. When I integrate 12, I get 12 times x. When I integrate x, I'm going to have 1/2 x squared. Again, just following that, add 1 to the exponent, divide by the new exponent. This will be a 1/3 x to the 3rd. And then we're evaluating that from 0 to 3. These problems tend to get like a little numerically messy, but I wouldn't simplify. I would just plug stuff in. Maybe simplify the parts that are easy to do in your head. I can do 12 times 3 in my head. So I would probably do 12 times 3 would give me 36. 3 squared is 9, so I would write that as 9/2. 3 cubed is 27, but I can divide that by 3. Oh, I said 9/2, and then, yeah, I said 9/2. 9/2. And if I plug in the 3 cubed is 27, but times 1/3 would be a 9. For completeness, I'm going to show that I am actually plugging in the 0. So 12 times 0, 0 squared, 0 cubed, those are all going to go to 0. A lot of times these area problems are not going to come with a picture. So let me write one the way that we might encounter it without a picture. I'll move it, I'll slide it up in a second. Find the area of the region. Found by y equals I don't know how messy to make it. It's like our second problem. Probably not crazy messy, right? Y equals x squared minus 3x and y equals x minus 5. Plus 5. I think. It is hard for me to make stuff work out and factor nicely. But I think that's gonna work. Okay. Do you want to see this with or without a picture? I'm good either way. Okay. So like I would say, if you wouldn't be drawing the graph on your own, then let's develop the skills to do it without a picture. Okay. So I'm going to do it completely without a picture. If I have to find the area of the region bound by these two graphs, I know there are a couple pieces that I need. I need to know where do they intersect. Because that's going to give me my limits of integration or the bounds for the integral. And I need to know who is on top. Because inside of my integral, I know that that height piece is going to come from doing the top function minus the bottom function. And we can figure both of those things out without drawing a picture. We can also figure both of those things out by drawing a not a very good picture. But I'm going to start with no picture at all. So if I'm going to do this with no picture at all, I'm going to start with where do they intersect. So I'm going to set the two functions equal to each other. And if I did this correctly in my head, it's going to work out. I need to shove everything to one side to get a 0. And I'm going to have x squared minus 4x plus 5. Oh, no, it was a plus 5. It already was a plus 5. Okay, so it's minus 5. Okay, that's better. That's going to work. So now this should factor as x minus 5 times x plus 1. Also, if I didn't mention this before, if you're not quick with factoring, quadratic formula really is your friend, because even if it factors, it just means that what's inside the square root in quadratic formula works out nice. So don't like get stuck trying to figure out how something factors. Use your skills, just quadratic formula it. Now I've got two values, 5 and -1. Here's the fancy trick to figure out who's on top without a graph. I just need to pick. So they intersect at -1 and at 5. Someone pick a number between -1 and 5. At x equals 4, I just need to know which function has a bigger y value. So I'm going to go y equals 4 squared minus 3 times 4. And I'm going to have y equals 4 plus 5. So over here I get 9. Over here, that's 16 minus 12. So that's 4. This is bigger. So the line is on top. And now I can set up the integral. I'm going from -1 to 5, and I need the line minus the parabola. One thing just to be careful about when you're doing the problems is to make sure that if you have more than just one piece, that you're distributing the minus sign through. And then if you can combine like terms after like you distribute stuff out, then it means there's less work on the integration side. So there's a question in the chat about where the x equals 4 came from. We can pick any number between -5 and 5. So this was like our randomly chosen number, but we're just gonna pick a number in here. Pick some test point. Yeah. Oh, I said I'd show you how to do it with a bad graph also. You're not going to get something totally crazy. If you get something totally crazy, they're going to give you a graph. For anything else, it's not going to be totally crazy. That parabola, concave up or concave down? Positive slope or negative slope? Great. Concave up parabola, line with a positive slope, lines on top. That's what I would do, right? I wouldn't really mess with the algebra. It only gets hard to graph these if you're trying to like actually put them on the axes where everything goes. If we just think about what the shape of the graph looks like, it's usually enough. We have 3 minutes left. Anyone have something random they want to do in these last 3 minutes? Shall we say it's Friday and gorgeous outside and we should just walk away? Do we want one last trig integral? Nah, I'm reading the room. I'm reading the room. Okay, there is a request to solve this one out all the way, so I'm going to do that, but totally respect it, folks, just if you're over it and want to move on with your life. I like really don't have enough room on this page. So when I flip the page, this is always where I make mistakes. -1 to 5. Maybe I can manage to do this. So -1 to 5. We had an x plus 5 minus 3x dx. Okay. Cool. Oh, that got a little smeary. I like these pens because they're erasable, but if I don't give them just a second to dry, they don't do so well. Okay, I'm going to distribute that minus sign through. So I'll have x plus 5 minus x squared and then minus -3x. Minus a negative, so that's plus 3x. You can go straight to integrating right now, but I'm going to combine my like terms first. So I'm going to think about this as 5 minus x squared plus 4x. The only thing that that part really does for me is it means I have one fewer term that I have to plug bounds into. So integrating that, I'm looking at 5x minus 1/3 x cubed plus 2x squared. I took the 4 and since I was going to be dividing by 2, I just did that math already. And we're going from -1 to 5. Again, I'm only going to do the parts that are easy to do in my head and the rest I won't simplify. 5 times 5, I got that. 5 to the 3rd, I happen to know. If you don't know that that's 125, then don't worry about it. Just put in 5 cubed. 5 squared is 25, and I multiply that by 2, and I get 50. And now I'm subtracting, plugging in -1. -1 times 5 gives me a -5. -1 cubed. Oh, you know what? Forget it. I'm just putting it in parentheses and not worrying about simplifying it because I'm not going to simplify that. I'm going to walk away. Good times. I'm really out of time now. So thank you all for hanging out with me. I like this stuff. I like this stuff way better than the early stuff we were doing. So, you know, it's all good.